Hi physical science students, welcome to the next video. This one's about ionic bonding. Ionic bonding is caused by the strong electrostatic attraction between the positive ion and the negative ions. And by strong electrostatic attraction is the force that two unlike charges experience between each other. Two unlike charges, a positive ion and a negative ion for example, experience quite a strong force to go together towards each other, and it actually is what holds ionic substances together, is the attraction between positive and negative charges. And so in ionic bonding, where the bond is actually that electrostatic attraction between the positive and negative ions. Now, compounds formed due to that electrostatic attraction are called ionic compounds and will consist of a metal bound to a non-metal with a couple of variations thrown in. An example of an ionic substance is calcium fluorite, CaF2. Looks like this. It's a crystalline substance, nice cubic form, and then has this lattice structure where the positives may be represented by the green, I think, and the negatives represented by the blue are attracted to each other, so you have these forces of attraction that hold it together. There's nothing actually in between them, there's no scaffolding or anything, it's just a force of attraction. You can think of it as an invisible force similar to magnetism. You can't see magnetic fields or magnetic forces, but you can experience them if you've ever tried to put two north poles together on a bar magnet. Electrostatic attraction is the attraction due to the charges. Ionic compounds are also known as salts. We've said that before, and they are made up of what's called, their structure is an ionic network lattice, and by lattice we mean scaffolding, or it's a recurring unit or structure that can be seen reoccurring. So we're not talking about two ions joining together, we're talking about millions and millions of them joining together to make this lattice type structure. And it's a network because all the bonds are going throughout it. It's not two-dimensional, it's three-dimensional. And it's lots of positive cations and negative anions, thousands and millions of them. Overall, the network lattice is neutrally charged, because there should be a cancellation between the positive charges and the negative charges. So overall, the ionic compound should be neutral. And these ionic compounds, even though the network lattice is made up of millions and billions and billions of cations and anions, they would have a formula, and this formula corresponds to the smallest whole number ratio of the cation to anion. So something like sodium chloride, when you have a crystal of sodium chloride or just table salt, it's made up of billions of positive and negative ions, but the simple recurring ratio of those positive and negative ions is NaCl, so one sodium to one chlorine. It's not a molecule. When we deal with covalence, you'll recognize, or hopefully you'll recognize, that when we give a formula for an ionic compound, it's not a molecule, it's the lowest or the smallest whole number ratio of the cation to anions. They also can have an empirical formula, which is the same as the formula in our case. Here's an example. Consider the reaction between sodium and chloride. There's our sodium chloride again. Explaining it using electron shell diagrams plus a simple equation. So here's our sodium with an electron configuration of 281. Here's our chlorine, which has 287. So that's our metal, that's our non-metal. The sodium wants to lose one electron, there it is. The chlorine wants to gain one electron, so it jumps across to here, represented by, there's a bit of words, you can pause that and read that if you like. Then it becomes the ions, so we have the sodium ion and the chlorine ion. So this is called an electron transfer. It's transferring from one atom to another. They're not being shared, they're being transferred to form these ions. and there's our formula. Na plus Cl minus goes to NaCl, and again it's charge balanced. This is just another diagram showing exactly the same thing, but this time they've shown the protons in the nucleus, and you can see that the proton number doesn't change, and they compare. In this case the sodium has gone to the electron configuration of neon, and the chlorine has gone to the electron configuration of argon. And in this case they've drawn them with what's called a Lewis diagram, and we haven't done Lewis diagrams yet, but we will, and it's a way of representing the electron configuration, but only the outer shell electron. So here is your single electron in your outer shell there. Here's your 7 electrons. Here's your 7 electrons there, shown like so. And then when they form the sodium ion, that has a empty outer shell or a full outer shell, depending on which way you want to draw it. So in this case they put a plus sign there, and in this case they've shown the full outer shell gained and the minus. We don't recommend writing it like this in physical science. However, we will learn how to do Lewis diagrams in the future. What's this? Using electron shell diagrams and simple equations, consider the following ionic compounds and explain the bonds between their atoms using electron shell diagrams and simple equations. This is sample problem 4.3, so you'll find that in your textbook. First one's magnesium oxide. There's magnesium, there's the oxygen. In this case, an electron transfer of 2 are shown. So when you draw this, you need to show the electron transfer occurring. You also need to show the resultant ions with their full outer shell and their electron configuration. The simple equation in this case is, now we go from Mg2 plus and oxygen 2 minus to magnesium oxide, that plus that. Next one is magnesium fluoride. Now the magnesium wants to lose 2 electrons, but the fluorine only want to gain 1. So in this case the simple solution is you have 2 fluorines. And if you're getting lazy, you could actually just write 1 fluorine, and let's see if I can actually get, you could write times 2 there. Saves you a bit of drawing, but you've got to make sure you're very clear with what you're actually trying to say. Let's get rid of that. So there's our atoms, and then of course what do we need to show next? Our ions. Okay, there's our fluorine ions and their full outer shell, and then writing the equation, we're going from magnesium, 2 fluorines, magnesium fluoride, MgF2. Now we should be able to construct that formula just by using our table of ions and either the crossover technique or the balancing technique, but this is just if you're asked to draw the electron transfer diagrams, this is what you're asked to do. So you should be able to now do these questions in your textbook without too much trouble, and we'll then, once you've done those, we'll be looking at the next video, which is the structure of ionic solids.